So you've probably heard the term redox reactions and immediately thought, oh boy, not this again, right? But what if I told you that you've been a redox expert your whole life and you just didn't know it? Today, we are going to untangle this whole topic so simply, you'll wonder why it ever seems so complicated. Let's jump in.
Think about it for a second. That reddish-brown stuff that's slowly creeping over the metal on your bike? Yeah, that's a classic redox reaction, and it's happening right there in front of your eyes.
Or how about this? The very act of being alive. You know, breathing, that process of taking in oxygen to create the energy that's powering you through this very moment. Yep, you guessed it. That's probably one of the most important redox reactions on the planet.
And that little jolt of panic you get when you see your phone battery hit 5%? Well, the very process that powers your phone and the reason it eventually runs out of juice is all driven by these reactions. They are, quite literally, everywhere.
Okay, so let's be real for a minute. Why does this one topic seem to trip everyone up? It's that one chapter in the textbook that makes even the most confident students just stop and take a deep breath. I totally get it. It feels like you're being hit with a dozen new rules and ideas all at once.
And let's be honest, this slide kind of captures the whole feeling, doesn't it? First, the definitions themselves can feel like a maze. Then, bam, out of nowhere, you're hit with all these oxidation numbers, +2, -1, +7, and you're sitting there thinking, hold on, is this a chemistry class or a math class? And don't even get me started on balancing the equations. That can feel like trying to solve a Rubik's Cube blindfolded.
But here's the thing. The core concept is actually incredibly simple. I want you to forget all the complicated rules for just a second. At its heart, chemistry is just about atoms trying to get stable. And one of the main ways they do that is by giving and taking electrons from each other. That's it. That's the whole story right there.
So here's how this little trade works. It's a perfectly balanced deal. When one atom loses an electron, we call that oxidation. Now, when another atom gains that very same electron, we call that reduction. And this is the crucial part. One cannot happen without the other. An electron can't just float off into space. It has to be grabbed by another atom. They are a total package deal. That's why we literally mash their names together. Reduction and oxidation become redox.
So how do you keep this straight in your head forever? You want to know the secret? It's this simple phrase right here, oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. I'm serious. Burn this phrase into your brain. It is the single most powerful tool you will have for this entire topic. It's a game changer.
Now, this next part can sound a little backward at first, but stick with me, it'll make sense. The atom that loses its electrons, the one that gets oxidized, is called the reducing agent. Why? Well, because it causes the other atom to be reduced. Think about it this way. A travel agent doesn't travel for you. They arrange travel for someone else. A reducing agent causes reduction in something else. The exact same logic applies to the oxidizing agent.
Okay, let's tackle the part that scares everyone the most, oxidation numbers. But I want you to reframe this right now. This is not scary math. It's just simple accounting. Think of it as a tool we use to keep track of which atoms are losing electrons and which ones are gaining them. It's our electron scorecard. And as you can see, these aren't just random rules you have to memorize. There's a really simple logic to them. Take a look. A pure element? It's always 0 because it's perfectly balanced. It hasn't traded any electrons yet. A simple ions number is just its charge. That one's a freebie. And the other rules follow that same kind of thinking. For a neutral compound, all the numbers have to add up to 0 because the whole thing is, well, neutral. See? It's just about applying a little logic. Okay, let's put this into practice with a real example. We need to find the oxidation number for sulfur here in H2SO4. Let me break this down. First, we know from our rules that hydrogen is pretty much always a +1. We've got 2 of them, so that gives us a total of +2. Next, oxygen is a -2. We've got 4 of those, which gives us a total of -8. Now, the whole molecule is neutral, so everything has to add up to 0. So we've got +2 from the hydrogens, plus whatever sulfur is, plus -8 from the oxygens, and it all has to equal 0. A little simple algebra tells us that sulfur has to be +6 to make it all balance out. See? Just a little logic. All right, now that we have the fundamentals down, let's see how these reactions actually show up out there in the wild. They generally fall into one of 4 main categories.
Broadly speaking, you're going to see 4 main types. You've got combination, where A and B come together to form AB. Simple enough. The opposite of that is decomposition, where AB breaks apart. Then you have displacement, where one element basically bullies another one out of the way and takes its place in a compound. And you should pay attention to that one, it's a favorite on exams. And finally, you have the weird one, disproportionation. This is where a single element somehow manages to be both the giver and the taker of electrons in the exact same reaction.
All right, it's time. Let's move on to the final boss, balancing these complex equations. It can look really intimidating, I know, but we're going to use a clear, step-by-step approach called the oxidation number method. And trust me, it turns chaos into order.
Okay, let's walk through this whole method, one step at a time. Don't let the equations scare you. Step 1 and 2. First, we assign oxidation numbers to everything, just like we practiced. When we do that, we see that copper goes from a 0 to a +2. Its number went up, which means it was oxidized. Meanwhile, nitrogen goes from +5 all the way down to +2. Its number went down, so it was reduced. Okay, step 3 and 4. Now we look at the change. Copper lost 2 electrons, and nitrogen gained 3. To make this exchange fair, the number of electrons lost has to equal the number gained. The smallest number that both 2 and 3 go into is 6. So we'll need to multiply the copper part by 3 and the nitrogen part by 2. Step 5 and 6. And this is the final piece of the puzzle. We use those multipliers, the 3 and the 2, as the main coefficients in our equation. We pop them in front of the right substances, and then we just balance the rest of the atoms like we normally would. And just like that, what looked like total chaos is now perfectly balanced.
Okay, we've gone all the way from rusting bikes to balancing these crazy equations. That's a lot of ground we've covered. So to make sure this all sticks, let's condense everything we've learned into one final super simple cheat sheet.
This right here is your cheat sheet. That's all it is. Oxidation is loss of electrons, and its oxidation number goes up. Reduction is gain of electrons, and its oxidation number goes down. And if you ever forget, just remember our good friend, oil rig. This little table holds the core logic of the entire chapter.
So, here's the big takeaway. Redox isn't just some abstract chapter in a textbook. It's the hidden chemistry that explains why things rust, how your phone gets its power, and even what's keeping you alive right now. So my question to you is this. Now that you can see this invisible dance of electrons happening all around you, what everyday thing will you never look at in the same way again?